Hey everyone, so this is a new experience for me, a new experience for my students. You are going to be getting a glimpse into my living room, something that I don't think any other students have had. I'm going to go through and try to solve some problems for you guys, go through the Doppler Effect equation. This might help to clarify some things with you guys. So I'm going to try my hand at movie editing. We'll see what happens. I think I'll have to make this in a series of clips. But yeah, hope you guys are all getting outside at some point. I just went for a run. It's nice out there. And just so you all know, we have someone who's helping me make this video. Hi, Newton. So yeah, he's been chilling on the couch with me. He I think likes that I'm home. I'd rather be in school with you guys. So this is the hardest equation probably that you guys will do in the near future. There's a lot of different things going on here. So as you can see, if you look at slide 48, F0, that is the original frequency. So that's the frequency that's being emitted by whatever is making the sound, whether it's a horn or a train or something like that. F prime is the observed frequency. So that's what it appears to be to the observer. So when we're doing this formula, there's three different V's here. So this V without a subscript next to it, this is the speed of sound. So the speed of sound will either be given to you in the problem, or you'll have to find that using the speed of sound formula for different temperatures. V0 is how fast the observer is moving. So if the observer is stationary, obviously that will be 0. And if they're moving, their speed goes there. And Vs is the speed of the source. So that's the speed of whatever is emitting the sound. So with these pluses or minuses here, both in the numerator and in the denominator, you only use one at a time. So if the source is moving, the speed of the source goes down here. And so we had learned in the notes, you guys might have watched the video on it. If you didn't, that was okay. Is that if the source is moving towards the observer, what's going to happen is that those wavefronts are going to bunch up. So when the wavefronts bunch up, the wavelengths get smaller. When the wavelengths get smaller, the frequency gets higher, a higher frequency or a higher pitch. So if we want a higher frequency or a higher pitch, since this is on the bottom, we're going to use subtraction in the denominator if the source is moving toward the observer. If the source is moving away from the observer, we're going to use addition, because if it's moving away, the wavefronts are going to get further apart, which means the wavelength will go up and the frequency will go down. So lower frequency, lower pitch. So we're only going to use one of those at a time. If Vs is 0, then it doesn't really matter. For V0, V0 is the speed of the observer. So the same thing kind of happens. If the observer is moving towards the source, again, the wavefronts are going to bunch up, which means they're going to get closer together, so a smaller wavelength, which means the frequency will increase. So if we want our observed frequency to go up, we're going to have to use addition on the top. If it's moving away, the wavefronts are going to spread out, which means bigger wavelength and smaller frequency, so we're going to use subtraction. So basically the way you can think about it is the one that's on top, here in the numerator, the positive or the addition, in the denominator, the minus or the subtraction. The one that's on top is if it's moving towards, and then the one that's on the bottom, the minus sign down here on the numerator, the plus sign down here in the denominator, that would be if it's moving away. Okay, so now I'm going to try to record myself going through and working out example 3. I'm not exactly sure how this is going to work. I don't really have a stand for my phone, so if I cut anything off, if you can't see the whole paper, I apologize. I'm going to give this my best shot. I did show the work for example 3. I put like a text in there, but just in case you want to see it worked out step by step. So example 3 has the source moving at 20 meters per second. And it emits a frequency of 256 hertz. Wants to know the frequency a stationary observer would appear. So here what we're trying to find is the observed frequency. So that is f prime. So that's what we're trying to find. And in this problem, it gave us the speed of sound. So we didn't have to calculate that at all, which is nice. So the speed of sound, which is letter V, we're going to put that in for V both on the top and on the bottom of this equation. So 343 meters per second would go here and on the bottom. Okay, so as far as what to do next, this tells us that the source is moving. So the source is Vs. So if the source is moving, we're going to plug something in down here. It doesn't tell us anything initially about the observer, but then it goes on and asks the frequency of a stationary observer, which means the speed of the observer is 0. So you can either put in plus 0 meters per second, or you can omit that because plus 0 doesn't really matter. So now, since the source is moving towards the observer, that means that the frequency is going to increase. Remember, like I said, if it's moving towards, we want this sign that's on the top. So we're going to use subtraction, because when we subtract something on the bottom, it will make our value here go up, because we're dividing by a smaller number. So we're going to subtract the speed of the source. So the source here is moving at 20 meters per second. Okay, and then we're going to multiply that by the original frequency. So the original frequency given in our problem is 256 hertz. So we will put that here. Okay, you will then go to your calculator. You will calculate that. I'll do that really quick. If you want to watch, you can. If not, you can just skip forward. So we'll have 343. Oh, and I messed up there already. Divided by parentheses, 343 minus 20. And you will see that this will give us a number greater than 1, which is what we want because our frequency is going to go up. So if we know our frequency is going up, this number should be greater than 1. So that's what will be inside the parentheses. And then we're going to go ahead and multiply that by our original frequency of 256. And you should get an answer, a frequency of 272 hertz. And that is, if you look at the next slide, if you look at slide 52, that is our answer. So our answer here, f prime, or the frequency, observed frequency by the stationary observer, is 272 hertz. Again, this question has 3 sig figs, so that's what we're going to round to.